this question here, and it's really important that we read this very carefully. So we have that a car is driven on a straight road, and the distance traveled by the car after time t is given by a quadratic function s. So now let's understand that first part. Basically, if I have a time, right, like let's say a time 2 seconds, right, t equals 2, then s of 2, the y value, will give me the distance that the car has traveled after how far it's traveled after 2 seconds, right? And if t is 3, then s of 3 will give me the distance that the car has traveled after 3 seconds. Now, of which of the following, which gives the best estimate of the velocity of the car? Now we need to know. Velocity is the change in distance over the change in time. It's a rate of change of distance. It's the rate of change of distance. Okay, so rate of change. Okay, and we want at an instantaneous time. We want at 6 seconds. So we want which one gives us the best estimate for the instantaneous velocity of the car at t equals 6. And the best estimate, okay, is going to be the shortest average velocity, closest to t equals 6 seconds. So what would be the shortest time interval, right? Closest to t equals 6 seconds. And that is going to be, so if I draw a picture just to illustrate this problem, make sure everybody understands, right? If I have my axes, right? And the velocity problem is the easiest one to understand. So here's t, and then here's the distance that the car has gone. I don't know what it is at, these values, but we're investigating what it is near 6 seconds, right? And then let's say that this is 5, and let's say that this is 7. Now after 5 seconds, the car has gone some distance. I don't know what it is other than that it's s of 5. Because s gives me the distance that it's traveled after t seconds for any t. I also don't know what it looks like, so maybe the curve of the car goes like this. This is the position of the car at any time. If I want to find the best estimate for how fast the car is moving at exactly t equals 6, right? I want to find out how fast it's moving there. If you imagine s of 5 being some value, I don't know what it is, but let's say that you've gone after, it's 5 seconds, and then the other one is measured in feet, so I don't know, maybe 1,000 feet. Okay, and then maybe s of 7 is, I don't know, 1,500 feet, for argument's sake, 1,500 feet. Okay, this is just my argument. Now, what would be the car's average velocity? Well, it went how far? It went 500 feet in that time period, right? That's the change in its distance, right? That's the y2 minus y1 over the change in the time. It went 500 feet in what time period? In a 2-second time period. T2 or x2, this is the x-axis, x2 minus x1. I'm just showing you that it's the slope of this secant line here, right? And in my case, right, what do I have? I have that it went, just thinking about this, it went 500 feet, right? It went from 1,000 feet to 1,500 feet. That's 500 feet in the time period from 5 seconds to 7 seconds, in 2 seconds. So it's moving pretty fast. It's moving 250 feet per second. Okay, because 500 over 2 on average in that time period. Now, if I wanted to find out its instantaneous velocity at exactly 6 seconds, right, I would sit here and I'd make this interval smaller and smaller. I would say, between 5.9 and 6.1. But that's not one of the options. I want to find the best estimate. So I basically want to find the shortest time period. And this here doesn't give me anything really. That there is is from assuming that it starts off at 0, the car. It gives me, its average rate. It doesn't mean anything. This here gives me its position at 6 seconds. This is not right. I don't want its position at 6 seconds. I want its velocity at 6 seconds. Okay. Now this one gives me its average velocity between 4 seconds. Let's say this is 4. And 8 seconds over here. It would give me the average velocity. Average velocity between 4 and 8 seconds. And you should see that. You should just make sure that that makes sense to you. This last one, though, gives you the average velocity. Between 5 and 7 seconds. And that's the average velocity between 5 and 7 is the closest to being the instantaneous velocity at 6 seconds. Right? Oh, and it even says that it's a quadratic, so my graph is not at all representative of this function here. But that's fine. I mean, it be what it is. I mean, it doesn't matter. It doesn't really matter. You'll get this question correct if you don't use that bit of information that's quadratic. But I could have drawn a little bit more accurate graph by making this orange curve here a parabola. But I mean, irrelevant. The point is that here, right, if I actually do another graph, so let's just take my time real quick. I'll do a rough sketch. T, and then D, and then here's my quadratic now. So something like that, let's say. And I have 5, and then 7 over here, and then 6 is in between the two. And now I have this point right here, and then this point right here. Now the slope of the line joining those two is closest to the slope of the tangent line. So the tangent line looks like this. That's the tangent line, that blue line at 6 seconds. And the slope of that tangent line is the instantaneous velocity at t equals 6. Now, I could draw the secant line, and that secant line is as close to the tangent line as I can get with the choices I'm given. So the secant line looks something like this. That's the secant line joining these 2 points, and that's as close as I can get to the tangent line. And I compute the slope of that secant line, and it's this D choice right here. And then that is your final answer.